Okay, so let's get right into it. You've seen the videos, right? A gigantic rocket booster, after yeeting a satellite into orbit, just falls out of the sky and lands perfectly upright. It honestly looks like something from a movie, but it happens so often now it's almost become normal. So today, we're going to pull back the curtain and break down the absolutely mind-bending physics and engineering that make this whole thing possible.
And when I say it's become normal, I mean it. We're talking more than 300 successful landings for the Falcon 9 first stage. Think about that. 300 times. A piece of hardware that's as tall as a 15-story building has come back from the very edge of space to land safely on its own feet. That is just staggering.
And in that, right there, is the million-dollar question. Because that's what a rocket is during landing. It's basically a giant, super top-heavy pendulum that is, by its very nature, fundamentally unstable. So, how on earth do they pull it off?
Well, to really get the answer, you first have to appreciate just how massive this challenge is. We're not just talking hard. From a pure physics standpoint, this should be flat out impossible.
This is the heart of it all. It's a classic challenge in engineering called the inverted pendulum problem. And what it means is that physics literally wants this thing to fall over. Every single force, wind, tiny vibrations, you name it, is actively trying to tip it. Without some kind of constant, active correction, it's going to fail. Every time.
Here's the best way to get a feel for it. Go grab a broom and try to balance it upright on your palm. See how you have to constantly move your hand, making tiny little adjustments to keep it from falling? Okay, now imagine that broom is 47 meters tall. That's taller than the Statue of Liberty, and it weighs 26 metric tons. That's the problem they had to solve.
And it's not even just one problem. It's actually three huge challenges that all have to be solved at the exact same time. First, you've got attitude control, just keeping it pointed up. Be off by even 1 degree, and it's game over. Then there's trajectory. You have to steer it back to a tiny landing pad from miles away. And finally, velocity. You have to slam on the brakes, going from hypersonic speed to a walking pace, all at once.
So how in the world do you tackle a problem that complex? Well, you can't have a human do it. You have to build a system that can think and react and correct itself way faster than any person ever could. You basically have to give the rocket a brain.
And that brain is called the GNC, which stands for Guidance, Navigation, and Control. Think of it as an incredibly powerful flight computer that's drinking from a fire hose of data, making thousands of tiny adjustments every second to keep that rocket perfectly stable and right on target.
The speed of this thing is it's hard to wrap your head around. The rocket's sensors are checking its orientation 1,000 times every single second. 1,000 times a second, it's asking itself, am I tilting? Am I spinning? Where am I pointing? That's how fast it can feel what it's doing.
And based on all that feeling, the GNC's brain makes a decision and sends out a command about 200 times every second. So it's this constant loop, feel, think, act, 200 times a second all the way down to the ground. It's that ridiculous speed that keeps our inverted pendulum from tipping over.
Okay, so a fast brain is great, but a brain needs muscles, right? It needs a way to actually do something. So how does the rocket physically make those corrections? How does it steer? The answer is, well, it's as simple as it is awesome. It steers with fire.
The tech is called thrust vector control, or TVC for short. Basically, instead of the engine being bolted rigidly to the rocket, it sits on a massive joint, a gimbal, that lets it tilt and swivel. By changing the angle of the engine's fire, it can literally push the bottom of the rocket around to keep the top balanced.
And you'll be surprised, it doesn't take much. That huge engine can only tilt about 5 degrees in any direction. But that tiny little nudge at the bottom of a 47-meter-tall lever creates a huge amount of force at the top, allowing for incredibly precise corrections.
And this brings us right back to our broomstick. The thrust vector control system is the hand in our analogy. Those constant, tiny, super fast movements of the engine nozzle are doing the exact same thing as the little micro adjustments your hand makes, perfectly balancing the whole skyscraper-sized structure on a pillar of pure fire.
So we've got the GNC thinking, we've got the TVC steering, but the rocket is still hurtling toward Earth at a terrifying speed. And this brings us to the final, the most dramatic, and the most perfectly named part of the whole landing sequence.
Now, the official term is a hover slam, but pretty much everyone who works with these things calls it the suicide burn. The logic is really simple. Fuel is heavy, and heavy is bad. So to save as much weight as possible, you want to fire that landing engine for the shortest amount of time you can. And that means you wait until the absolute last possible second to light it up.
So why the dramatic name? What makes the timing so incredibly unforgiving?
It's because there's no do-over. There's no time to hover and adjust. The whole maneuver is calculated so the rocket hits zero speed at the exact same instant it hits zero altitude. Light that engine a fraction of a second too early and you run out of gas while you're still in the air. A fraction of a second too late, well, you just don't have enough time to stop before you become a crater. The margin for error is razor thin. And yet, somehow, the GNC system nails it. After solving this insane physics problem in real time while falling through the atmosphere and steering with fire, the rocket pulls off the suicide burn and touches down with an accuracy of about 1 meter. Just incredible.
And this right here really brings it all home. Look at these numbers. A landing speed of just 2 meters per second. Those 1,000 hertz sensors feeding a 200 hertz control loop, that tiny but mighty 5-degree gimbal, and a final accuracy of 1 meter. These are the stats that turned an impossible physics problem into a routine Tuesday.
Which really just leaves you with one final thought. You know, just a couple of decades ago, this was pure science fiction. People said it couldn't be done. But with some brilliant engineering and a whole lot of computing power, here we are. It just makes you wonder, if we can solve this, what other impossible problems are out there right now that are just waiting for the right solution?